Hello and welcome back. Let's continue with our program of foundation engineering. Still on chapter 1. I think previously we talked about critical state of clay. It was part of clay model, okay, modified clay model, and we have talked about this critical uh, critical state, the critical state line. This one in 2 dimension and 3 dimension, okay, and we have talked about these surfaces. So knowing when the failure of clay will happen is good, is okay, but we need now to understand, to know how to use those information, critical state, the failure criteria of clay, how to use it in a numerical analysis in a FEA formulation, because this is what this part of this chapter is about, how we do FEA formulation. Okay, so to do FEA analysis, numerical analysis, FEA formulation, we need relationship, stress strain relationship. Okay, and the numerical analysis, the numerical modeling is using this stress strain relationship to calculate and give us result. Okay, so this is what we are going to talk about now, stress strain relationship for yielding clay. Okay, so normality condition, which is also associated flow rule in plastic theory, is saying that plastic flow vector is normal to the yielding surface, and this is at the stress point corresponding to any stress state. Okay, so then using that statement, okay, based on this reference derives the relationship, plastic stress strain relationship for clay yielding on this surface. We talked about this surface previously, a state boundary surface. As we said, on this surface also, failure happen on this surface also. So using that, we have this relationship. You see, this is strain, this is stress increment in P and Q, CP and Q here. So we need to link what is the relationship between stress and strain, so that for each increment of stress, we get the corresponding strain. Okay, because as you know, stress is caused by maybe force that will be applied on the foundation. The charges, the forces coming on the foundation will cause the stress, and this stress will cause strain or deformation if you want. So knowing the limit of deformation we want, we then can understand, can judge the bearing capacity of our foundation, because in all the design, there is limitation for strain or deformation, okay, that is accepted. So based on that, you can judge that this is the ultimate limit state, the ultimate bearing capacity of your foundation. So anyway, this relationship is very important for FEA formulation, for in the FEA analysis. So I will keep this equation here. In this equation, this coefficient is just the ratio of Q and P. This P here, Q here. Okay, the mean effective stress and the shear stress. Okay, and the ratio is the ratio of these Q and P on the current state on this surface, state boundary surface. Okay, so this equation also can illustrate the shear volume. See, volume is here, right? The shear volume coupling phenomenon of the occurrence of volumetric strain as well. Okay, and this is due to the shearing stress. So we can see this kind of thing. I mean, this situation is noticeable in the case of granular soil, for example, medium dense and dense sand. Okay, and we will discuss this in the following section, 9.2 and 9.3. As you can see here, we are on 9.1. 191 is for clay. Okay, next section means in the next video we will talk this kind of relationship, like model that will is appropriate for granular soil. Okay, because this is for fine soil, clay. Okay, so this relationship is very important because we need it. And you know, this M is just here. I think I don't need to tell you that again. M is just the slope of this. Okay, and we also talk about this VP and this lambda previously. So anyway, if we have this equation, this is the equation we need to have, we need to know to do our FEA formulation. And the equation is useful because it can be used in this D matrix. If you remember in section 1.8, this is section 1.9. In section 1.8, we did talk about D matrix. What is D matrix in FEA formulation? Okay, so I will just put this as a reminder. This is the section 1.8. We talk about this. Okay, this D matrix is the link between stress and strain. And this is what all FEA formulation need. Okay, this is necessary in any FEA formulation. And we gave an example. We did this before. Okay, this is just a reminder. We gave an example of D matrix in case of like a element that exhibit elastic behavior in plane strain condition. This is an example of D matrix. Okay, and as you can see here, this, for example, looks similar to this matrix. Don't you see? This is just like link between stress and strain. It's similar so to this condition. That's why this relationship is important. We need this relationship for FEA analysis. So that being said, if you are using CAM-CLAY model in your any soft you are using CAM-CLAY model, technically you are using this relationship, even if you don't understand. The software is using this relationship. So what you need to do, however, is to provide some information to this software so that it will be able to calculate, give you result. And what you need to provide are just this information. For example, M, what is the value of M of your clay? Because we saw that this M is slope is a soil parameter. Okay. So here is then the lab test needed to determine all soil parameter you need for calibration of your CAM-CLAY model. Okay. So this table 12 is showing model parameter that must be evaluated for calibration of your modified CAM-CLAY model. Okay. What does this mean exactly? It means that if you are going to build your foundation on clay soil, okay, and you intend to use numerical analysis to model, to predict the behavior of your foundation on this clay, on this soil, and you want to use the clay model, then you need to give the soft some information about your soil, because soil are different. So these are the information, these are the parameters that your soil, your soft needs these parameters. You have to provide them. These parameters are changing according to the type of soil. They are different for each soil. Okay. So you have to go take some soil sample on the field where you are going to build your foundation, and go to the lab and run some tests and obtain these soil parameters. Okay. So the M can be obtained from triaxial test. Okay. And it is used for normally consolidated clay or over consolidated clay. Okay. This lambda, you can see it here, can obtain it from isotropic consolidation. It's done for normally consolidated clay. Okay. The N, K, H. H is just the slope of the, let me go back a little bit to show you. K, just a minute. Yeah, this is H. See, this slope, or here, the slope of this surface. See? So anyway, before using clay model in your numerical analysis, you need this parameter for calibration. Okay. So that will be the end of this clay, modified clay model. We are going now to talk about another model. Okay. I hope it's clear for you the clay model. Okay. We will continue with the same way for modeling numerical analysis. Okay. Here is another model, the cup model. This cup model, now we are 9.2. This cup model is for other type of soil. Maybe it can be used for clay as well, but because this model is just collection of many models, okay, and it developed by these references, okay. So the model has been used for many mechanical behavior to investigate, represent many mechanical behavior of many geological material like sand, clay, rock, and these under high and low pressure conditions. So here is the model, cup model, and as you can see, it has a lot of curves and lines. So we need to determine a lot of equations to be able to determine, to deal with this model. Okay. So as this figure shows, this cup model consists of terrain hardening elliptical cup, this one, you see, and also elastic perfectly plastic cracker powder failure surface, this line. Okay. So the thing is, this model need to be plotted in this I1 versus J2 plot. The I1 is, this one is actually the first invariant of stress tensor, which is sigma in the X plane plus sigma Y plus sigma Z. Okay. And J2 is second invariant of the vectoric stress tensor, okay, given by this equation. So in this equation, as I said, sigma, tau, they represent normal and shear stress. Maybe you know that already, I hope. Okay. And on this plane, X, Y, and Z plane. For triaxial axisymmetric stress state, we can say that I1 is 3 times P. Do you remember what P is? P is the mean effective stress, which means sigma 1 plus sigma 2 plus sigma 3 divided by 3. Or again, if we consider that sigma 2 is equal to sigma 3, then we can say that P is sigma 1 plus 2 times sigma 3 and divided by 3. Okay, so we can consider that sigma x is like P but on the x plane. Sigma y is P, like the mean stress on the y plane. And sigma z is the mean stress, means P on this z plane. So that means it's P plus P plus P because we are in this situation, axisymmetric stress state. Okay. In that case, all of them will be same. So it means like 3 times P. Okay. So as you can see here, we have 3P. So we can replace this by I1. Okay. The first invariant of the stress tension. And J2, if we check this one, if we do square root of this J2, we can obtain the sharing stress, Q. So this one also can be replaced by square root of J2. Okay. So what we need is to express mathematically this model. Okay. This is what we need. And in this CAP model, the soil behavior is assumed to be linear elastic inside the yield surface, inside. It's linear elastic, but on the yield surface, the soil is assumed to deform plastically based on, of course, associated flow rule. Okay. Similarly, like in case of camp clay. So this CAP model is used as constitutive model in many FEA formulation. Okay. And this is because the model is able to represent like many type of soil in many situations. For example, in like in case of modeling share in this dilatancy behavior, which is in over-consolidated clay or dense sand. Okay. Then the strain hardening cup will provide help. Okay. This will give a good, will allow to obtain this kind of situation, to model this kind of situation. But if you take the case of like sharing induced compression behavior, like in normally consolidated clay or loose sand, then in that case, this model can also help to numerically simulate that kind of behavior. That's why this model has been used for as a constitutive model for FEA formulation. Okay, we need then to represent the model mathematically, okay, with questions. First, let's go with this line, the Tracker-Parker failure surface. For this surface, this equation 62 can be used. Okay. So the equation of this line is this equation. And for this line, horizontal line, vomit, this equation is used. Okay. So we need Q plus this is this coordinate. Horizontal line. And for the large cup, this one, okay, this equation is needed. And you can see here, this point is very important, the coordinate of this point, because this point is where the connection between this cup and this Tracker-Parker, this failure surface, happen. So we need to identify the coordinate of this point, which are this L, N, and this one. As you can see, these are included here. Okay. And of course, the R. The R is also included. So the next one is this small cup, small one. That one is given by this equation. Okay. And the last one is the tension cutoff. This one. We need this vertical, this limit. Okay. So as you can see, this limit, it just the tension, the traction that the soil can support. As you know, soil is not strong to stand against tension. So very small. Actually, concrete also. Okay, so all these equations are needed to represent this cup model. Okay, so I will put them, all of them here. Okay, so this one is the Tracker-Parker, and this one is the vomit. This one is the large cup. Okay, this one is for small cup, and this one is for the tension cutoff. Okay, so this xn, which is in here, means in the large cup. Okay, the equation of the large cup one is given by this equation. Okay, D and W, as you can see, and this one are also necessary. The alpha in the Tracker-Parker model can be obtained using this equation. Okay, and you can see easily that this is just depending on soil parameter. You see phi here, right? The only unknown parameter is phi here, and phi is just depending on the soil parameter. Okay, and this kappa, still in the Tracker-Parker, is obtained by this equation. And also, you can see this also is depending on the soil parameter phi. Okay, D, Y, and R, you can see D here, Y here, and R is in here and here. These are soil parameters, and these need to be determined, investigated through lab test. Okay, this parameter is just accumulation of plastic volumetric strain. Okay, sigma of this one. So I will put this equation here. If you remember this is the D matrix for Camp-Clay, modified Camp-Clay model. Okay, we did just now okay, the previous section. So this relationship, the relationship of this for cup model, all these equations can also be used to express, to obtain this kind of relationship, means stress strain relationship, so that we can use it in FEA formulation. Okay, so the main advantage of using this kind of relationship is that the finite element modeling of foundation is they give convenient mechanical mechanism to include the plastic deformation of soil in design consideration and allowing the formulation of more realistic and economic design methodology. Means these are very important for reliable numerical analysis. Okay, so all the equations for this cup model are here, and as you see, there are some soil parameter that we need to determine for calibration of this cup model. So for the calibration, this cup model, here are the soil, the lab tests we need. Okay, D, you can see D here. Okay, this D can be obtained from isotropic consolidation and can be used for normally consolidated clay or loose sand, because this cup model can be used for both. Okay, this alpha in the Draka-Parker failure surface, it's here. Triaxial test, because as you see, this alpha is just based on phi. You need triaxial test to obtain the phi soil, the internal friction angle. Okay, so this for normally consolidated clay or loose sand. Okay, kappa, R, W, and T. T is just normal. This is like traction, the maximum traction force the soil can support, which is small. So all type of soil are here, the lab test corresponding and the soil parameter that are here. Okay, T is here. Okay, W, you can see W here. Okay, R is used in both here, the large cup and the small cup. Okay, so I think that will be all for this cup model also. So we have finished with the modified cup clay model, and also for we have also started and completed the cup model. Remember that cup model can be used for several types of soil, including clay and sand, loose sand, dense sand, and clay also normally consolidated clay or over consolidated clay. Okay, that will be all for this video. Thank you very much for your time, and see you next time.